All right, today we're going to dive into this one single powerful idea that is just everywhere in mathematics. We're talking about continuous mappings. You can think of it as this unbroken thread that connects points, shapes, and even some of the most profound theorems in analysis. So let's see just how deep this thread really goes. So we all think we know what continuous means, right? But what does it really mean, in a mathematical sense? How can we be 100% certain that a function is totally smooth and connected with absolutely no tricks or hidden gaps anywhere? You remember that trick from high school, right? Just draw the line without lifting your pencil? And look, it's a great way to start thinking about it, but it's just not rigorous enough. When we're building real mathematical models of the world, we need a guarantee, a definition so incredibly precise that there's no room for doubt, no matter how far you zoom in. Okay, so here's our game plan for building that certainty. First, we'll lock down the core no-jump rule. Then, we'll see how that one simple rule actually preserves the fundamental shapes of things. From there, we'll get to the big payoff. Two incredibly powerful theorems that continuity guarantees. And finally, we'll look at an even stronger, more bulletproof version of this whole promise. So let's jump right into section 1, the no-jump rule. We're going to take our everyday gut feeling about what continuous means and sharpen it into a rock-solid mathematical tool. This is the foundation for everything else we're going to talk about. You can see the classic visual right here. On the left, a continuous function. It's like a smooth road. You pick points that are close together on the path, and their values are also close together. But on the right, you've got a discontinuous function. It's like the road just has a cliff or a big pothole. The path is totally broken. And this is really the heart of the formal idea. Continuity is basically a promise. It says that if you pick any two input values that are super close to each other, I guarantee their output values will also be close. There's this direct relationship between input closeness and output closeness. That's the no-jump rule, right there. So what's the big deal with this no-jump rule? What does it actually get us? Well, as we're about to see in this next section, it has some amazing consequences for the very shapes and sets that functions act on. It preserves their most essential qualities. I love this metaphor. Think of a continuous function as a magical piece of rubber. You can stretch it, you can bend it, you can warp it into all sorts of new forms, but you can never, ever tear it. The fundamental wholeness of the original shape is perfectly preserved. So what exactly gets preserved? Well, a couple of super important things. As you see here, if you start with a connected set, basically one solid unbroken piece, its image after a continuous mapping will also be one solid unbroken piece. Same goes for a compact set, which is just a fancy way of saying a set that's contained and includes its own boundary. This is so important because it stops functions from shooting off to infinity or having values that get closer and closer to some limit but never actually reach it. Continuity makes sure these properties stick. And really, it all just boils down to this. This is the essence of what continuous mappings do. They transform things without breaking them. Simple as that. Okay, this is where it gets really cool. Let's see how this one simple idea builds into something even more powerful. In this section, we're going to explore two massive theorems where this simple no-tearing rule leads to some incredible, almost magical results. First up, the Intermediate-Value Theorem. I know, it sounds a little academic, but the idea itself is stunningly simple. If you have a continuous path that starts at one height and ends at another, you are guaranteed, 100% guaranteed, to pass through every single height in between. There are no exceptions. This is a huge deal in physics, for example. It tells us that an object moving from point A to point B has to occupy every single point in between. Here's a super simple way to think about it. Imagine you're standing on one side of a river and you walk to the other side. As long as you don't teleport or fly, meaning you walk a continuous path, at some point, you absolutely must step in the water. You have to pass through the space that exists between the two banks. That, right there, is the Intermediate-Value Theorem in action. And the second cornerstone is the Boundedness Theorem. You'll sometimes hear it called the Extreme Value Theorem. This one is another amazing promise. It says that if you have a continuous function over a finite, closed chunk of space, there will always be a highest point and a lowest point. Always. It's like this. Imagine you go on a hike that starts at mile marker 1 and ends at mile marker 5. As long as you stick to the trail, no helicopters, right? It is an absolute certainty that there was a highest point you reached on that trip and a lowest point you reached. Continuity guarantees that those extremes have to exist. But wait, there's more. For some really tough problems, even the powerful promise of continuity isn't quite enough. And that brings us to our final section, a stronger guarantee. Here, we're going to see why mathematicians needed an even more reliable, consistent version of our no-jump rule, and it's called uniform continuity.
The thing is, the standard definition of continuity is a little shifty. The amount of closeness you need for your inputs to guarantee closeness in your outputs, well, it can change depending on where you are on the function. And for some problems, that's just not good enough. We need a single standard of closeness that works everywhere, no matter what.
And this slide just lays out the difference perfectly. Standard continuity over on the left, that's a local property. It's a promise that holds true point by point, but the exact terms of that promise might change as you move around. Uniform continuity on the right is a global property. It's one single one-size-fits-all standard of closeness that is true across the entire domain. It's a much stronger, way more robust guarantee. So, let's pull this all together. What's the big picture? This idea of continuity, this unbroken thread, it gives us a rock-solid, precise way to say no jumps allowed. And from that one simple rule, it preserves the very nature of shapes, it guarantees these amazing results about intermediate values and extreme points, and it serves as the absolute bedrock for building mathematical models we can actually trust. And by the way, if you want to really, really get into the weeds on this, everything we've talked about is explored in fantastic detail in Chapter 4 of Marsden and Hoffman's classic text, Elementary Classical Analysis. It's a phenomenal resource if you want to go deeper. And that's what I want to leave you with. We started with a really simple, intuitive idea, no sudden jumps, and we watched it blossom into these powerful, predictable theorems about how the world works. It really makes you wonder, doesn't it? What other incredibly simple rules might be out there, secretly governing our universe, just waiting for us to find them?